All right, let's graph secant, cosecant. We're going to try to do this quick. Are you ready? Are you on the ball? Because today can go quick if we're ready. All right, I'm going to draw the unit circle. I've got 4 points I'm going to refer to. 1, 0, 0, 1, negative 1, 0, and 0, negative 1. You tell me. Is sine the x value or the y value? So where is sine equal to 0? For what degree measurement? For what radian measurement is sine equal to 0? 0, radian, pi, 2 pi, 3 pi, so on and so forth, right? All good there? Well, what's the relationship between sine and cosecant? Reciprocals. What's the reciprocal of 0? Undefined. So therefore, cosecant, here's what we know about the graph. This is the first thing we learn about the graph. Sine is defined for all angle measurements. You can plug in any angle measurement, you're going to get an output. But cosecant, that's not true. Cosecant's undefined for 0, pi, 2 pi, 3 pi, and for all of those values. So if cosecant's undefined at those spots, what do you think is true about the graph of those spots? There's a vertical asymptote at those spots. Very good. Okay, so first thing we learn about cosecant, it has vertical asymptotes. Now cosine, is that the x value or the y value? X value. So where is cosine equal to 0 then? So on and so forth, right? The relationship between cosine and secant is that they are reciprocals. So therefore, the reciprocal of 0 is undefined, and secant will be undefined at pi over 2, 3 pi over 2, 5 pi over 2, so on and so forth. So therefore, if we graph y equals cosecant of x, we start by doing this. We start by graphing y equals the sine of x. That's the foundation. The graph of sine of x will unlock all the characteristics about cosecant. Sine of x goes up to 1 and down to negative 1. Its period is 2 pi, and we divide it up into 4 parts. And I sketch the sine graph. Where does sine start? It goes up to 1, and so on and so forth. So far, I have not yet sketched cosecant. I've only sketched a rough graph of sine. As I now look at that graph, I'm going to insert asymptotes. The asymptotes will occur wherever cosecant of x is equal to 0. So you can see that at negative 2 pi, I have a vertical asymptote. At negative pi, I have a vertical asymptote. At 0, I have a vertical asymptote. At pi, I have a vertical asymptote. At 2 pi, I have a vertical asymptote. What do you think? We all good? Have I sketched any part of the graph of cosecant yet? So here is where you have to think critically if you want to understand why in the heck the graph looks the way it does. What is the height of the sine graph here? What's the reciprocal of 1? positive 1. Reciprocal does not change sign, simply value. Okay, so we'll just flip. So the height right here is 1. So if we take the reciprocal of 1, we get 1. You take a reciprocal, it doesn't do opposite value. Okay? It doesn't go to negative 1. It's not a vertical reflection or anything like that. Okay, so it turns out that sine and cosecant share 1 point in common. The sine of pi over 2 is 1, and the cosecant of pi over 2 is 1. Okay? I'm going to go just barely to the right of 0. Would you say that the sine graph has a large positive value or a small positive value? What is the reciprocal of a small positive value? A large positive value, something like up there. I'm going to go just to the left of pi. Do I have a large positive value or a small positive value? And the reciprocal would be a, so you can see that it does that. Well, it trends up towards infinity. Okay, right here, what's the height of the graph right here? What's the reciprocal of negative 1? So they share that value in common. And we would use the same type of logic about reciprocal of small negative numbers become large negative numbers in order to generate that. And that will just repeat itself all the way around. And that then is the graph of cosecant. The graph of cosecant is simply a bunch of U-shapes that sit on the maximums or minimums of the sine or cosine function. You understand where the graph comes from? Let's now try graphing some stuff. We'll get rid of that one. And we'll get rid of that, and we'll just do 2 examples. And I think because you're an extremely intelligent class, we will figure this out. Okay? We're going to graph a slightly different problem here. We're going to graph y is equal to negative 3 secant of 2x plus 2. Okay? So I'm just going to step up the level of difficulty for us because I don't think we're going to have a problem with this, especially since we did a checkpoint together. I think we're going to do fine. Okay. I start by graphing y equals negative 3 cosine of 2x plus 2. That's what I start doing. Okay. That's going to be the key to me making a secant graph. I'm going to look for the vertical shift, the amplitude, the period, and the horizontal shift. I always look in that order. What is the vertical shift of this graph? 2. What's the amplitude? So what's the maximum value of this function? 5. So I'm just going to put 5. Oh, I'm not even going to do that. We're going to... I'm trying to make it so 5 isn't all the way at the top. Why am I making it so 5 isn't all the way at the top? Yeah, I got to have room for the rest of the function, right? And I'll go down 5. So I went down 5, but what's the minimum value of this function? Negative 1. Olivia? You got it? Vertical shift is 2. From 2, I'll go up 3 to get to 5. And I'll go down 3 to get to negative 1. Better? Okay. So I have this horizontal axis that goes through a value of 2. Horizontal axis that goes through 2. I now have the vertical structure of my graph taken care of. I'm going to go all the way up to 5. I'm going to go down to -1. The vertical part is taken care of. Let's now do the horizontal structure of the graph. What's the period? Pi. I'm going to mark off pi. Pi over 2. Pi over 4. 3 pi over 4. Yeah. And the reason why is we actually use that in calculus. So without a doubt, it comes up. The number of times I've done a calculus problem or an AP exam problem where it is important to know those pieces. It's definitely there. Okay. Is there a horizontal shift? Awesome. Always makes my day when my trigonometric functions don't have a horizontal shift. I mean, that's all good. So. Let's graph it. Where does it start? -1. It's going to go up or down from there. It's got nowhere to go but up. Because it's cosine, it's going to start the maximum or minimum. We good now? William? Okay. And now I draw my asymptotes. And here's where you have to call me a liar. Say it. Say it with being mean and nasty. Okay, all right. Wow. Yes, I'm a liar. I told you look for where the graph crosses 0, but that's not entirely true, okay? You look for where it crosses its axis of rotation, and that's where you draw the asymptotes. So if you think about it, Grace, suppose instead of a +2, suppose it was a +8. That graph would sit way above the x-axis, wouldn't it? Well, then it would never cross, so you don't draw any asymptotes, right? No, that's incorrect. We do draw asymptotes. The deal is we don't draw it here where it crosses the x-axis. We draw it here where it crosses the axis of rotation. Your vertical shift. See how it's rotating back and forth on that axis? Your horizontal line. Yep. So the asymptote goes there, 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 and there. You need to draw a good graph, yes. Now, what do I do to finish this off? I look at where the graph crossed this axis. And it crosses at -3 pi over 4, at -pi over 4, at pi over 4, 3 pi over 4. Better? I draw my U-shapes. And some of you might say, well, Mr. Gens, that's a really sloppy graph. I mean, how accurate could that actually be? I think I have it already typed in here. If I go into y equals, there's my graph. Looks like I need to do a +2, though. I go over here, we got a +2 on the end there. Must switch the problem because you guys are super smart. And I press graph. And, you know, does that look like, I mean, okay, rate me on a scale of 1 to 10. My graph. My graph. A strong 7? That's all I get? That my graph just gets a strong 7 out of 10? Oh my gosh. Wow. Okay, this test is going to be hard. All right. I'm done. We're pulling the punches. You guys are rough crowd. All right, last one. What's different about this one? It's got all the shifts. Yep, it's got the horizontal shift in with it. I want you guys to know, yeah, you got to be careful. Yeah, I've made many mistakes in my life. You know? It's got all the shifts in it. You could really kind of, it was really a really shifty situation. Thank you. Thank you. I know I've sworn at least a half a dozen times on YouTube without knowing it. I mean, it's just happening. Yeah, we're sorry, YouTube Nation. Should be adult content. There we go. Okay, so yeah. All right, so just to pause for a second, if you looked at this problem at the very beginning of this class, you know, when we started the section just last Friday, you would have said, that looks impossible, right? But now, easy for us, because we're all going to Harvard. Let's do it. All right, what is the vertical shift? 2, amplitude, 4. So therefore, Olivia, what is the maximum value of the graph? All right, I'm going to give you a chance to give your final answer. And what is the minimum value of the graph? -2. All right, good job. Way to go. You got it. All right, so we're going to go by twos. 2, 4, 6. Sorry to put you on the spot. It is rough when teachers do that. So I was taking a chance. Thank you. And I have a horizontal axis of rotation. Grace, that's my new favorite phrase for you, okay? Horizontal axis of rotation is what I just drew. And it's going to go up to 6 and down to -2. To bother you. All right. What's the period? Pi. All right, sweet. I don't know. Free country. Do what you want. I made extra space because I knew I had a horizontal shift in play. And I think in the original problem, the horizontal shift was twice what I actually have right here. And so we needed a lot more space. I'll add some more. Okay. Do I have a horizontal shift? What is it? Thank you. -pi/4. You got to solve the inside equal to 0. So 2x plus pi/2 is equal to 0. So whereas 2x equal to -pi/2, divide both sides by 2, and you get x is equal to -pi/4. How much of a tick mark is pi/4? To the left. Now, you guys are used to doing this, and this is where you have to key in, because I'm going to save you some time. We would generally make a ghost graph, right? Well, then all of a sudden we would have a ghost graph and another ghost graph for the ghost graph, and that just seems like a lot of work, right? So let's not do that. Are you ready to press on without the ghost graph? Watch. Cosine would start at what value? -2. And would you go up or down from there? I'd go up. So instead of starting here at -2 and going up, I'm going to start at -2, but I'm going to move. And then I go up. Now, some of you are saying, whoa, Mr. Gens, that just made horizontal shifts really easy for me. And I wish you would have shown me that earlier. Well, I've tried that in different years, and it seems like a number of students make a lot of mistakes unless I teach everybody kind of the ghost graph method. So if you were doing that on your own, great, good for you, I'm happy for you. But in order for me to try to ensure learning for the group as a whole, that's the strategy I use. So all of a sudden now, I didn't need a ghost graph. I just simply shifted everything back pi over 4 units. We good? What's my next step? Asymptotes. And what is my last step? Make the U's. GG. Okay, YouTube Nation, as I said, make the U's. Some of the students thought we should start drawing sheep. So, as in, U's are sheep. So, okay. Right. So secant, cosine, that tells us where we start. Exactly. Okay. Now, real quick, which part of the graph is actually the graph of secant? Just the red. And someday when you look at the red, you're like, boy, how do they get secant out of there? And you see the cosine graph going right in the middle of it, right? Okay. Secant or secant? All right, very good. All right.